name's Lian. Today we'll be talking about role for stiffness in vascular fate. McCloskey Lab specializes in the differentiation of human and mouse stem cells into the cardiovascular lineages here. My project focuses on the differentiation of endothelial cells, which line the lumen of blood vessels and are an essential component to building microvasculature in vitro. There are many factors in the microenvironment that affect stem cell fate. I am looking at physical cues, such as substrate stiffness, to direct stem cell fate. Oops, wait, what's going on? Do you guys see background with like a pink and a yellow thing?
Yes.
Yes? Okay, sorry, okay. Back in 2006, Engler showed that substrate stiffness has an effect on stem cell fate. By matching the substrate stiffness to physiological conditions, cell fates were directed towards its specific lineage. In the body, brain tissues are one of, oh wait, do you guys see my, okay, yeah. In the body, brain tissues are one of the softest, while bone is one of the stiffest. Plastic petri dishes are normally used to culture cells, which far exceeds the stiffness found in vivo. Engler was able to show that by matching the substrate stiffness, he was able to derive brain-like cells on soft substrates and bone-like cells on stiff substrates. Do you guys, wait a minute, what is going on? Okay, Engler's study was the inspiration for this study where we want to mimic the signals found in the vascular microenvironment. It has been reported that smooth muscle cells right here have a reported stiffness of 5 kilopascals, and endothelial cells have a reported stiffness of 1.2 to 2 kilopascals. It's also been shown that in diseased endothelium, there's an increase of stiffness compared to healthy endothelium. So we wanted to investigate how vascular progenitor cells respond when plated on an elastic substrate. Will they be directed towards an endothelial or muscle cell fate? To better visualize the vascular differentiation on varying substrate stiffness, our lab has generated a new mouse embryonic stem cell line called ESC-A3 and B2. We bred a mouse with a green fluorescent protein under type 2 that marks for endothelial cells, and a mouse with a red fluorescent protein under alpha-synuclein actin, which marks for muscle cells. The blastocysts are cultured on mouse embryonic fibroblasts, and over a course of a few days, the inner cell mass appears and is replated on the feeder layer and expanded. These cells allow for real-time observation of the vascular differentiation process. To characterize these new stem cells, we looked at typical colony morphology, as well as high levels of this alkaline phosphatase activity, and normal karyotypes of 40 chromosomes each. We also checked for typical stem cell markers like OCT3-4, SSCA1, SOX2, and NANOG, which all express on both stem cell lines. Next, we checked for pluripotency by injecting the stem cells into a nude mouse to form teratomas. The teratomas were examined for the differentiation of cells from all 3 germ layers. So here we see epithelium of the digestive organ found in the endoderm, dermis tissue found in the ectoderm, and muscle tissue found in the mesoderm. We then wanted to confirm the appropriate expression of these markers by staining the teratomas with an endothelial marker, beta-catenin, and a small cell marker, small cell actin. These beta-catenin positive cells form muscle-like structures which co-localize with the type 2 GFP in both lines. And this is also seen for the small cell myosin heavy chain state, which co-express with the alpha-synuclein actin RFP cells. Next, we generated embryoid bodies to analyze the co-emergence of the morphological features and the reported expression from day 7 to day 21. Type 2 expression under GFP is first observed at day 7 for the A3 line and at day 10 for the B2 line, followed by the alpha-synuclein actin RFP expression surrounding these structures. I think hopefully these videos will play. So these videos are Z-stacks of the day 18 embryoid bodies. And towards the end of observation at day 18 and day 21, we see that these previously larger vessel-like structures seem to be remodeled into smaller, more compact structures. Lastly, we induce a differentiation of endothelial and muscle cells using our staged serum-free induction method to examine the expression of the reporters over time. We quantify the temporal expression of the Tie2 GFP and alpha-muscle RFP expression using fluorescent activated cell signaling. We observe peak fluorescence of both reporters occurring at day 10. Again, wait. Oh! Okay, using our, sorry, it's like laggy between the two screens. Using our serum-free induction method that's been highly optimized for these cell lines, we plate our stem cells onto fibronectin-coated plates for 3 days and sort for a mesodermal marker, FLIC1, and then replate these vascular vagina cells onto our varying substrate stiffness plates. So normally these cells are cultured on plastic petri dishes, which has a stiffness in the gigapascal range. And to mimic physiological stiffness, our collaborator, Dr. Engler at UC San Diego, provided these chips called zebra axes. Zebra axes are made out of a polyacrylamide hydrogel that have zebra-like stripes, which vary in stiffness. So here we'll have a soft stiffness, and then next to it will be a stiff, and then it'll alternate in stripes. This allows the cells to be in the same environment and migrate towards their preferred stiffness. These are confocal images of live A3 vascular vagina cells that have been differentiated for a total of 11 days. Here we have two different zebra axes, 1 versus 10. Wait a minute. Why is it showing the wrong thing? Do you guys see like two images? There's like 1, 10, 10, 34?
Yeah. Yes.
Okay. I'm seeing this one.
I know, we're seeing that one.
That one.
So just go to the next one.
Okay, so these are the live ones. And here you can see that there's a lot of these Tie2 GFP positive cells that are kind of look like they're balled up. So here, 4 days later, on day 15 of differentiation, I fixed and stained the cells with an endothelial marker PCAM1 and a stilcell marker SM22 alpha and DAPI for the nucleus. As you can see, the cells don't adhere very well to the zebra axes, but where they do attach is on this 10 kilopascal stripe. And you can also notice that there might be a slight height difference of 2 to 5 microns in between the two stripes. But then on the 10 versus 34 zebra axes, we see that the cells are actually plated on the 34 kilopascal stripe and not the 10. And there's also more cells that have adhered to this zebra axis chip. As a control, we decided to plate human umbilical vein endothelial cells, which is normally supplemented with serum. Here they are on an 11 versus 40 kilopascal chip, and on day 1 they have attached everywhere, but then by day 4 we see that they have migrated to the 40 kilopascal stripe. From these experiments, we would conclude that the vascular vagina cells prefer to adhere to the higher stiffness, but due to that height difference, we believe that it produces a rigid valley effect, which might be contributing more to the actual substrate stiffness, since we notice the cells will only sit on the higher stiffness stripes. But due to design limitations, the higher stiffness will always be higher than the softer one. So in longer cultures, oh, that's what's going on. There's a sorry. Okay, where was I? So we suspect that however, we do suspect that these lower stiffness is producing these Tie2 GFP positive cells that are balling up detaching. This might be due to them being directed towards a hematopoietic fate. So in order to remove the difference in height in between the stripes, we next examine the real stiffness on the single stiffness surfaces. Again, we induce these cells into the FLIC1 progenitors and plate these cells on either the tissue culture plastic, 40 kilopascal, or 10 kilopascal polyacrylamide gels. Here I have differentiated A3s and stained for PCAM-PE and calponin-1-FITC. PCAM-PE is for endothelial cells, while calponin-1 is for muscle cells. In some areas, you see that the cells organize themselves in a way where the endothelial cells are in the center while the muscle cells surround them, where other places we see pure populations of the PCAM positive cells or just pure populations of calcitonin 1 positive cells. So we see that on day 4 of differentiation, we see an increase of these PCAM positive cells on the lower stiffness, while we see an increase of the calcitonin 1 positive cells on the higher stiffness. By day 10, we see a decrease of these markers, but we still see the same trend. However, on day 14 of differentiation, we see that these calcitonin 1 levels drop dramatically, and our cells are mainly PCAM positive on all 3 substrates. In conclusion, we have generated a Tie2 GFP and alpha muscle actin RFP mouse stem cell line that gives us a tool to study vascular differentiation. Both the vascular progenitor cells and huvex prefer to sit on the stiffer regions, but we believe due to the topology of the zebra axes, this is affecting cell adhesion. We have found that the vascular progenitor cells generate more Tie2 GFP positive cells, but eventually detach, and we think this is due to directing them towards hematopoiesis. Once repeated on single stiffness surfaces, we find that low stiffness may generate more endothelial cells, while higher stiffness may generate more muscle cells. However, this is lost over time due to us culturing the cells in an endothelial-specific media. Substrate stiffness may be directing differential regulation of our endothelial and muscle cell populations, but we still need to verify that specific time window. I would like to acknowledge the McCloskey Lab and our collaborators for generously supplying the zebra axes, as well as IGRT for funding my graduate studies. Thank you.